Hello everyone, this is Professor Keen. Today I'll be talking about life under a sea of air. The reference is A Student's Guide Through the Great Physics Text, Volume 2, Chapter 17. This is a section continuing with the work of Pascal, his treatise on the equilibrium of fluids. This is Chapter 17, so chapters 14 through 18 are focusing on Pascal's work. So we're almost through with Pascal. So here's the question that Pascal is asking in this chapter. So are there limits? Well, there are some broad questions, but here's the question we'll start out with. Are there limits on the height that water can be drawn up using a vacuum pump? And we already addressed this to some extent in the last lecture, so this is somewhat of a continuation of the last lecture. But are there limits on the height to which water can be drawn upward using a vacuum pump? And I'll cut right to the chase. The answer that Pascal provides is yes. And as a way of describing this, let me draw a picture, and we'll consider how a well works. So pumping water out of a well. So let's suppose we have the ground right here and a deep well like this. And let's drop a pipe down into the well. And the idea is we're going to try to pump water out of this well. So we'll put right here a vacuum pump. So here's a pump. And the idea is the hope is to be able to pump this water out of the well. So let's put some water in the well. And the question is, what's the maximum height to which we can pump this water? And we find that when we turn on the pump, so when we turn on the pump, the water reaches a maximum height, a max height of, as Pascal says, about 31 feet. So the water, so if this well is more than 31 feet deep, then we're not going to get any water coming out of the pump. So the height here above the surface of the water is 31 feet. Why is this? Well, this is because the air pressure, and I should specify at sea level, that is, as long as this situation is right around sea level, is only enough to push the water up by about 31 feet. So what's happening here is, remember, the idea is not really that there's something in here sucking the water up. All the pump is doing is removing the air from this region right here. And then since we still live under this atmosphere of air, so this is the air up here, the air is weighing down or pushing down on the top surface of the water. And because this water here has air pressure pushing down from the outside, but no air pressure pushing down from inside, that unbalance pushes this water up, but the height of the air is only such that it can support a 31-foot column of water. So immediately this raises the question. So let me draw another question here. So how do we get water out of wells that are deeper? How do we extract water from deep wells? kind of a natural question that we may ask. And I guess there are a couple of answers, at least two answers. Here's the first answer, is you do it the old-fashioned way. You use a bucket and rope, right? You just drop a bucket down there and dip it in the water and pull it up, right? So do it the old-fashioned way. A second answer is to overpressurize, and this is the more common way to do this, overpressurize the chamber. I'll explain what I mean by this in a moment. The chamber with the water in it. Okay, so what does that look like? So let me redraw this scenario. So we've got, once again, this deep well like this. And what we do is, instead of using a pump, we use a compressor. So this is a compressor. And then what we do is we put a tube down here and we cap off the top of the well. We seal it, so make sure there's a nice like an O-ring or some high pressure seal right there, and we force air into, so here is the seal over the top. We force air of high pressure into the region that is above the water. So here's the water in the bottom of the well, right? So this is all the water down here. And then we force high pressure air into here. So if we put sufficiently high pressure in here, then what we can do is we can push the water out so that it comes squirting out the top. Right? So this is the situation, because after all, if we seal this properly, we can make this pressure of, oh, I don't know, 1 atmosphere, 3 atmospheres, 10 atmospheres, 100 atmospheres, however high pressure we want it to be. We just have to make sure we have a seal here that's strong enough to withstand whatever pressure there is. This, incidentally, is how many oil wells work. You overpressurize the region above the oil, and then the oil comes squirting out. This is also how cryogenic fluids, such as liquid nitrogen or liquid helium, are transferred from one place to another. So for example, from a dewar, it's like a big thermos bottle, to a cryostat. So that's a device used in low temperature physics. So you overpressurize, so you have a bath of liquid nitrogen or liquid helium, you put some high pressure nitrogen gas or helium gas in here and it squirts out. You use a tube and you deliver this over to your apparatus that you're trying to cool down. So that's just a little sidelight there. Okay. One of the questions that's interesting that Pascal raises, so let me write down another question here, is can a pump, this is a corollary question, so can a pump be used to siphon water over a mountain range? Over a mountain range. This is something that had been proposed apparently. I think he mentions Wherein of Alexandria, an ancient Greek, who was asking, can we perhaps do this? So you might imagine a situation where you've got, I'll draw it down here, I'm going to try to conserve space. Let's suppose we've got a lake and a mountain range and then a valley right here. And this lake has water in it like this. And the question is, can you take a tube, dip it in the water, have it go over the mountain range, and deliver the water down into a valley over here? So can you siphon this water? And the answer is yes, but only if the mountain range is less than 32 feet high, because after all, if you try to siphon it, you try to pump it, the water can only be pushed up 32 feet in this? So the answer would be, I guess, yes, a very qualified yes. So the answer is yes if the mountain ridge is less than 31 feet high, which few of them are. Okay. Now, there's some other topics that Pascal is going to talk about here. So let me point out some of the other questions that he raises. So here's another question. Does the maximum height of a fluid in an evacuated tube depend on anything else? So does the max height of the fluid in an evacuated tube depend on any other factors? So any additional factors? And the answer to this is yes, it does. So what are some of the factors that Pascal mentions here? Well, first of all, it depends on the density of the fluid itself. So for example, if you are trying to pump, instead of water, you are trying to pump liquid mercury out of this well. Well, because liquid mercury is much denser than water, it's heavier, and so the atmospheric pressure can only support about 2 feet, a little more than 2 feet and 3 inches of liquid mercury. So for example, you can only pump liquid mercury to a height of about 2 feet 3 inches, or about 760 millimeters, or 76 centimeters. And this is because its specific gravity, the specific gravity of mercury is 14. That is, it's 14 times, about 14 times as dense as water. So 1/14 the height, which ends up being about 2 feet 3 inches, or about 760 millimeters. So sometimes you'll hear that the atmospheric pressure is 760 millimeters of mercury, or 760 torr. Those are alternative ways of describing the atmospheric pressure. So the density of the fluid dictates how high you can pump it up, or more correctly speaking, how high the atmospheric pressure can push it up. It also depends on the density of the atmosphere, of the atmospheric air. And this is something that Pascal points out, is that when it gets humid, for example, there's water in the air, and so the air actually becomes more dense and it's heavier, and so the atmospheric pressure ends up being higher, and so the 31-foot column of water can actually vary by quite a bit depending on the humidity of the air. So the 31 feet of water can vary, and I think Pascal mentions by almost 2 feet. Okay. This is something that he mentions on, by the way, page 220. So he talks about this. So you can see here, this is how meteorologists talk about how much moisture there is in the air by the air pressure. Okay? And there's a third thing that the maximum height of the fluid in an evacuated tube depends on, and that is the altitude that you're carrying out the experiment. The altitude. Okay? So for example, Pascal mentions that the atmospheric pressure, this is, by the way, on page 225, he talks about this. He does an experiment where he measures the height of a fluid when you are in an evacuated chamber at the bottom of a mountain, and then he takes us up to the top of the Puy de Dôme in Auvergne, France, and he finds that the height of the fluid changes significantly when an altitude of 500 fathoms, he says, is ascended. To give a sense of how much the air pressure varies, I looked this up, that the air pressure at the top of Mount Everest, at the summit of Mount Everest, is only enough to support about 250 millimeters of mercury. And this is compared to 760 millimeters of mercury at sea level. So in other words, the atmospheric pressure at the top of Mount Everest is about 1/3 of what it is at sea level. So that's why it's very difficult to breathe, and oftentimes people need oxygen when they're hiking up to the top of Mount Everest. So let me, I think I'll pause right there. Next time, just as a preview for next time, I'm going to talk about Pascal explains how to measure the weight of our entire atmosphere, of all the air around the Earth. And I will save that for next time because I'm just about out of space.